Hello everyone, welcome back to my channel. I am Praniti Reddy from Sri Venkateswara College of Engineering, studying 3rd SEM in Bhaskara section. Today my topic is going to be operations on processes. Operations on processes. We delve into the essential operations that allow the operating system to manage and control processes. Get ready to understand the concepts behind process creation, termination, states, scheduling, communication, synchronization, and deadlock handling. These are the core functionalities that make modern computing possible. Process creation, fork system call, and access system call. The fork system call creates a new process that is a copy of parent process. This process begins execution at the same time as its parent, but the two processes run independently. The fork function is an essential tool for creating new processes that share the same code and data as the parent process, but with their own independent memory space. Access system call. The exec family of system calls replaces the current processes with a new process. This allows you to switch between different programs without creating new processes. The exec family offers efficient ways to load and execute new programs without unnecessary overhead. Process termination. Normal termination, abnormal termination, and external termination. In a normal termination, a process can terminate normally when it completes its designated task or reaches its intent endpoint. This is a clean exit and ensures that the process has finished its work successfully. Abnormal termination. An abnormal termination occurs when a process encounters an error or an unexpected condition forcing it to stop abruptly. This could be due to a system crash, a fatal error in the code, or a user initiated signal. External termination. External terminations happens when a process is terminated by an external event, such as a user intervention or a system administrator's action. This could involve killing a process, suspending its execution, or removing it from the system. Process states. First one, new. When a process is first created, it enters the new state. It is waiting to be loaded into memory and allocated necessary resources. This is a brief initial stage before the process actually starts running. Second step is ready. In the ready state, a process is ready to execute but is waiting for its turn to get the CPU. It's like a car waiting in a line at a traffic light, ready to go once the light turns green. Third step, running. The running state is when the process is actively using the CPU and executing its instructions. This is the most active state where the process is actually performing its tasks. Fourth step, waiting. The waiting state occurs when a process needs to wait for a specific event or resource to become available, such as waiting for input from a user or accessing a file. Fifth one is terminated. The terminated state indicates that the process has finished executing is no longer active. It is the final state signifying the end of the process's lifetime. Process scheduling. Shortest job first. Second step is process scheduling. Third step, round robin scheduling. And fourth one is multi level queue scheduling. Shortest job first. This scheduling algorithm prioritizes jobs with the shortest enlisted estimated runtime. This is a simple and effective approach, but it may not be ideal for processes with varying arrival times. Priority scheduling. In priority scheduling, processes are assigned priorities and those with higher priorities are allocated the CPU first. This allows critical tasks to be executed quickly, but it can lead to starvation of low priority processes. Round robin scheduling. This algorithm provides each process with a fixed time slice to execute on the CPU. After its time slice expires, The process is placed back in the ready queue and waits for its next turn. This is a fair approach that ensures that all processes get a chance to execute. Multi level queue scheduling. This approach divides processes into multiple queues based on their characteristics. Priority, input output bound or CPU bound. Each queue has its own scheduling algorithm. Different priorities on and responsiveness for different types of processes. Inter-process communication. Pipes. A pipe is a unidirectional communication channel that allows data to flow from one process to another. It's like one-way street for data transfer, often used for simple communication between parent and child processes. Message queues provides a more flexible and asynchronous communication method. They are essentially shared memory regions where processes can exchange messages without requiring direct interaction. Shared memory allows process to access a common memory space. This is highly efficient communication mechanism, but it requires careful synchronization to prevent data corruption. Semaphores. Semaphores are used to manage access to shared resources by multiple processes. They act as flags or signals that indicate whether a resource is available or not. Synchronization mechanisms. Mutexes, semaphores, monitors, and condition variables. A mutex means a mutual exclusion is a log that ensures that only one process can access shared resource at a time. It prevents race conditions and data corruption when multiple processes try to modify the same data simultaneously. Semaphores, as mentioned earlier, are used for synchronization and coordinating access to shared resources. They are more versatile than mutexes, allowing for more complex synchronization scenarios. Monitors provide a high level abstraction for synchronization and encapsulation and data and associated synchronization operations. Condition variables are used to signal events or conditions between. They allow processes to wait for specific conditions to be met. Simplifying synchronization logic. Deadlock handling. Prevention, avoidance, detection, and recovery. Preventing deadlocks involves ensuring that the necessary conditions for deadlock formations are never met. Deadlock avoidance aims to avoid deadlocks by carefully allocating resources based on set of rules and algorithms. Deadlock detection involves periodically checking the system for deadlocks. Once deadlock is detected, the system needs to recover deadlock. This can be achieved by preempting resources. Conclusion and key takeaways. Understanding the operations on processes is crucial for any aspiring operations system developer or anyone interested in how computer works. We have covered key concepts like process creation, termination state, scheduling, communication synchronization, and deadlock handling. As you dive deeper into the world of operating systems, remember that the efficient management of processes is fundamental to creating a stable and responsive computing environment. Thank you.